Hello and welcome to Conceptual Physics at Delaware Tech, Chapter 24, Magnetism. So in this unit, we're going to cover magnetic forces, just like we've already talked about electric forces. We'll talk about magnetic poles, that is the North and South Pole. This would parallel the quote-unquote polarity of electric fields with positive and negative charges. We'll talk about magnetic fields and magnetic domains, and then we'll talk about electric fields and how they're related directly to magnetic fields and how one can create the other. We'll talk about electromagnets, which are actually generated by using electric fields to create magnets. Then we'll talk about how magnetic force affects moving charged particles, and we'll talk about magnetic force on current carrying wires. These are wires that already have electrons flowing through them. Then we'll talk a little bit about Earth's own magnetic field. Earth is a giant magnet. We'll talk a little bit about that. And then we'll talk about the concept of biomagnetism. This is living organisms that actually have built magnets inside their bodies, and they frequently use these to do navigation. So the term magnetism actually comes from an ancient town, Magnesia. Magnesia was a town in what is now Turkey. It was the region known as Anatolia that was part of the ancient Greek Empire. And there were unusual stones that were discovered and described by Thales of Miletus. We've already been introduced to Thales of Miletus. He was the one who did the amber rod experiments with the fur, rubbing them to polarize it and create negatively charged rods and positively charged fur when he was studying electricity, living in the 6th century BCE. Now, the stones that were found, these unusual stones that are magnetic, are called lodestones. You may have heard of these. These are naturally occurring magnets. They're iron ore that the actual mineral itself has been aligned with its magnetic fields, and the whole chunk of metal acted as magnets. And in fact, much later than Thales of Miletus, in the 11th century, Chinese were known to make some of the first compasses using magnetic particles, magnetic needles. In fact, there's a writing that dates from 1088 AD where it was describing how Chinese were making these compasses for the first time. So electric static force, magnetic force, and motion. These are all related concepts. We've already talked about electric force. This is the force between two charged particles. If they're opposite charge, positive and negative, they attract. If they're the same charge, positive and positive, or negative and negative, they're going to repel. But that force between them, whether it's attractive or repulsive, is directly proportional to the magnitude of each of their individual charges. It's also directly proportional to the product of those charges, and we learned this from Coulomb's law. Coulomb's law also showed us that there is a direct relationship between the electric force and the distance between these charged particles. In fact, this is a relationship referred to as the inverse square law. We've seen this before. And the inverse square law basically says that force is inversely proportional to the square of the distance between the charged particles. So that means if you double the distance, the force will go down, but it'll go down not double, but fourfold, double times double, double squared. And likewise, if you brought the distance in, made it shorter, made it 1/2 the distance, you will increase the force fourfold. It's square of whatever the change in distance is, but in the opposite direction. If you increase one, you'll decrease the other. But Coulomb's law is not the whole story when we're talking about particles that are moving. When a charged particle is moving, that is when they're moving with respect to each other, they're moving towards each other, moving away from each other, moving by each other. Not only do you have electric force, but you have magnetic force. But the electric force itself, it's not a simple calculation. You don't just use Coulomb's law because they're changing their position constantly. So it's a bit more complicated. It's beyond the scope of this course, and so it depends on the motion, but the electric force will change in the process. But any moving charge, whether it's a positive charge, negative charge, if it's moving, and only if it's moving, and moving can be moving laterally, moving in a circle, spinning around, any kind of movement, will generate a magnetic field in addition to the electric field that's already present on the charged particles. So you can have moving charges in electric currents when the electrons are going around. You can have them when you're changing voltages and the energies of the electrons are making the electrons move in different places. You have electrons spinning inside within the atoms or near atoms in metallic elements, especially conductive ones. And any of these motions of a charged particle, mostly electrons for this course, any of these motions will generate a magnetic field in addition to the electric field that's already there. So the magnetic field induces the movement of electric charges. I just told you that the movement of the charges creates the magnetic field, but the magnetic field also creates movement in the electric charges, and that is electric current. And what you find is, if you look at a wave of light, and when I say light, I mean the general definition of light, meaning anything in the electromagnetic spectrum, from radio waves to microwaves to infrared to visible to ultraviolet to X-rays and gamma rays at the very high energies. All of these are electromagnetic waves, and they all are composed of two waves that are perpendicular to one another, and both of them are perpendicular to the direction of the wave. And you have one wave that is the magnetic field shown in red, and one wave is the electric field shown in blue. And I could have twisted this. I could have made the electric field wave vertically and made the horizontal wave the magnetic. Doesn't matter. They're both perpendicular to each other, and they're both perpendicular to the direction of the motion. But what this really means is that these two waves are manifestations of the same phenomena. They are both part and parcel of any electromagnetic wave. They are both composed of an electric wave and a magnetic wave, of an electric field and a magnetic field. And it turns out that a magnetic field can be used to create an electric field, and an electric field can be used to create a magnetic field, and they self-reinforce. So if you have one, you'll have the other if the charge is moving. So a magnetic force between a pair of magnets can be either attractive or repulsive. Just like when we have positive and negative charge, we have attractive electric force. If we have positive and positive charge, or negative and negative, we'll have repulsive force. The same thing with magnets. If you have, you can have both attractive magnetism, magnetic forces, and repulsive magnetic forces, and it's going to depend. This is very similar to what we see with the electric forces, and the strength of these forces will depend, just like electric field does, on the inverse square of the distance. So the inverse square law works here, but for distances between magnetic poles, between a north and a south for attraction, between a north and a north for repulsion, between a south and a south for the other repulsion. Okay, that force is inversely related to the square of the distance. So electric and magnetic forces, electric and magnetic fields, they're different aspects of the same phenomena we call electromagnetism. So magnetic poles, let's talk a little bit about that. Magnetic poles, these are what give rise to the magnetic force. You have a north pole of a magnet and a south pole of a magnet. It might be a bar magnet where one side is north and one side is south, or it might be a bar magnet that's been bent into a U shape where one end is north and one end is south as well. So there are two types of poles, the north pole and the south pole of a magnet. We're not talking about the Earth, we're talking about the north pole of a magnet and the south pole of a magnet. And it turns out these were named because the north pole of the magnet, if you put a needle, if you made a needle a magnet, if you magnetized a needle and you floated it in water, the north pole of the needle would point towards north, the direction north. And the south pole of a magnet, of a needle, would point towards Earth's south pole. Now you might think, well, wait a minute, you just finished telling me that north is attracted to south and south is attracted to north. Why is the north pole of a magnet pointing to the Earth's north pole? Well, I'm going to tell you a little secret. Earth's north pole is the south pole of Earth's magnet. We just don't call it that. So if I say the North Pole, and I'm talking geographically, I mean in the north, but technically it is the south pole of the magnet that is planet Earth. So we've already said this, like poles will repel each other. North will repel north, south will repel south, and opposite poles will attract. You've heard the phrase opposites attract. Well, this is true of both electric charges, plus and minus, and it's also true of magnetic poles, north and south. So you can't have one pole without the other. Now, an electric force, you can have a positively charged particle all by itself. You can have a negatively charged particle all by itself. Magnetism doesn't work that way. There is no such thing as a single pole. Every magnet has two poles. And in fact, for many decades, people have been trying to find the very elusive monopole. Physicists have been looking for this for a long, long time, at least 50 years that I'm aware of. And they haven't been able to find it. Some people think they can. Some people think they'll never find it. In any case, a simple bar magnet, a straight magnet, has two ends, the north and the south. And the horseshoe, it still has a north and a south. It's just bent like it's shown here. One end is north and one end is south. And what they're showing here with the red, these are the field lines. The field lines go from north to south. Just like when we were looking at positive and negative charges, they would go from positive to negative. In here, it's north to south. Okay, a weak and strong magnet repel each other. Okay, so you've got the same poles, the north pole of one magnet and the north pole of a weaker magnet, and they're repelling each other. The greater repelling force is by the A, stronger magnet, B, weaker magnet, C, both forces are the same, D, not enough information. Well, if you remember back when we were studying Newton's third law, they have to be exactly the same forces. Anytime two objects interact with one another with some force in between them, the force that object A exerts on object B is exactly the same force that object B exerts on object A. No matter how strong the magnetic field of this one is, and the magnetic field of this one is, no matter how strong the gravity of this one is compared to the gravity of this one, no matter how strong the positive charge of this is to the negative charge or the positive charge of this, it doesn't matter. Anytime two things are interacting, the forces they exert on each other are exactly the same magnitude, just in opposite directions. So this is just simple Newton's third law. And like I said, it's the same with gravity. It's the same with electric force. Any forces at all. You press against the wall is pushing you with the same force you are pushing it. Magnetic fields. Okay, so magnetic field is a region of magnetic influence. So this is influence at a distance. It's force through empty space, or it could be air, it could be some other matter. But these are force lines that will go through anything. And they surround each pole. So you have force lines coming out of the North Pole and force lines coming out of the South Pole. And the shape of the field is revealed by the lines that spread from one pole to the other. And so if you want to actually visualize this, actually see field lines or something that looks like field lines, you would just take either a bar magnet or a U-shaped magnet and sprinkle some iron filings on them. Iron filings are essentially little iron needles, and you sprinkle it around. They'll line up with the lines of the magnetic field, and you'll actually see what the field lines sort of look like based on how these little tiny needles of iron line up. And I'll show you a picture of that in the next slide. So by convention, we write our field lines from North Pole to South Pole, just like we did it for electric field from positive to negative. For magnetic, we agree to write them from North Pole to South Pole. And magnetic fields are produced by motions of electric charge in atoms or any other particles. Any particle with a charge that's moving will create a magnetic field. So if a charged particle is just charged and staying still, it'll have an electric field. Once it moves, it will have an electric field and a magnetic field. So okay, so here's a picture of a bar magnet, and somebody sprinkled a bunch of metal filings, iron filings, because iron can be magnetized very easily. If you sprinkle it on, you can actually do this. You could buy a bar magnet, you could buy iron filings and kind of dust them over, and you will see them line up, and you can see the lines, the curved lines that go from north to south, and as well as the lines that spread out from each of the poles. So from the north, you see lines that are curved in all directions around the North Pole. These are the magnetic field lines. These are the lines of force, and they're strong when they're close because of the inverse square law, and they're much weaker when they're further away because of the inverse square law. And we have that both on the North Pole and the South Pole of any magnet, no matter what shape it is. With this bar magnet, you can see them curved gently on the bottom and the top. But one thing you should know about fields, just like with electric fields, there are more lines when the field is stronger. And you can actually see that with my metal filings, with iron filings. You'll see more of these lines when you have a very strong magnet. The other thing is not only are they similar to electric field and electric field lines in the same way, but like electric fields and like magnetic fields, while we show them in 2 dimensions because somebody set a magnet on a flat table and then sprinkled filings around it, the fact is the magnetic field lines or electric field lines, when it's charges, are in 3 dimensions. It's not just going around in a loop, it's going around all directions around from any way you can connect north to south, on top of the table, below the table, on the above on the table, below on the table. Whichever way you look, there are connecting lines of force, of magnetic force here. So it's 3 dimensions, even though we usually just look at them as 2 dimensions. All right. So as I mentioned before, magnetic fields are only created when something is charged and that something that's charged is moving. You have to have those 2 conditions. So an electric charge is always going to be surrounded by an electric field, whether it's moving or not. If it's moving, it's also surrounded by a magnetic field. So magnetic fields are actually created by distortions in the electric field. And that is because the electric field is moving and it gets distorted, and that distortion creates the magnetic fields. Now, this is very advanced physics that was worked out by Albert Einstein in 1905. Albert Einstein published 4 very, very, very important physics papers in different fields, all in the same year. It was called the Annus Mirabilis, which means the miracle year. People have used that term for other things, but Einstein had a miracle year where he published 4 papers in physics that each revolutionized a different area of physics. And one of them involved magnetic fields being created because of distortions in electric fields when those electric fields are moving. So we have different ways to make electric fields, different ways to have charged particles moving. The most common particle that's moving for a magnetic field is the electron. Usually the protons are part of the atoms, and the atoms frequently aren't going anywhere, especially if it's in, say, a wire of copper or a wire of gold or silver or even iron. The atoms aren't staying anywhere, but the electrons are free to move. So it's usually the electrons we're talking about. And the electrons have lots of ways to move, but there are two main categories of movement for the electrons. They can actually spin right in place. And this is a major contribution to magnetism. There are certain atoms that have odd numbers of electrons, so that if they had 2 electrons, one may spin one way and one may spin the other, and the magnetic effects cancel each other out. But there are other atoms that only have 1 extra electron, and they have this magnetic field, or they might have 2 electrons that are separated in space in the atom, and they each have the same spin, and they each produce the same magnetic field. Now, when I say spin, it's not really spin. We talk about spin as if the electron is actually spinning. It's a term that physicists use because the behavior that actually happens is very abstract and very bizarre, but it behaves like it was actually spinning. But the electrons aren't technically spinning. We call it spin because the math that goes with it exactly mimics as if the electron truly was spinning. So when I say spin, that we'll call it spin, but it's technically not really spin. But that's one way electrons can produce movement and therefore generate a magnetic field. So the electrons spinning in the same direction will create a stronger magnetic field. So if you have a lot of electrons all spinning, say, clockwise, they'll all produce the same magnetic field that will add together, and you'll end up with a lot of magnetic field building up in that particular substance. You can also have a pair of electrons spinning in the opposite direction that I just mentioned, but those fields will cancel. So a lot of substances aren't easily magnetized. They don't have much of a magnetic field. You have other movements of electrons. You could have the electron actually moving, the whole electron moving, and that could be around a nucleus within a single atom, or it could be the whole electron moving somewhere else past other atoms in an electric current. Either one of those is movement of an electron. So all of these different types of movements will automatically create magnetic fields. All right, so the source of all magnetism is A, electrons revolving around an atomic nucleus. B, electrons spinning around an internal axes. C, either or both. D, tiny bits of iron. Well, we just mentioned both A and B can contribute to forming magnetic fields because both are movement of electrons. So it's either one or both of them. So in order to produce magnetic fields, charges have to move. And this basically comes in two versions. They either spin in place or they move completely, either around within an atom or they move within, say, an electric current, or they can be moving associated with other particles, but some kind of movement of the electron, any kind of movement will generate a magnetic field in addition to the electric field that's already there. All right. Magnetic field lines are more dense when the field is A, stronger, B, weaker, C, both, D, neither. Well, just like electric fields, we find that there are more field lines, they're tighter packed, they're denser packed when the field is stronger. You have more lines of force, more field lines, and that signifies that there are more lines of this magnetic force between one pole and another pole in a magnet, or between magnetic poles from different magnets. So what's going on in the magnets? Well, magnets themselves, physical metal magnets like an iron magnet, if you look at the internal structure of it, the crystal structure that makes up the iron in the magnet, you'll find little miniature crystals that are all packed together making this iron magnet, or whatever the magnet is made out of. And it turns out that each one of these little crystals may have be a magnet because the electrons are aligned within that little domain. We call them magnetic domains. But the domains are not all lined up, so each one is a magnet pointing from north to south in a different direction. And it might be composed of countless tiny little domains within a single chunk of metal, and they're all pointing in a different direction. When they point in a different direction, they just cancel each other out. So there's no magnetic field total for this entire magnet. Permanent magnets will actually have all of these individual arrows, these individual field lines going from north to south. They'll all be pointing in the same direction. And permanent magnets are magnets that will always keep that, even if you're not doing something to them. So permanent magnets can be made in a couple different ways. The classic way is to either take a piece of iron or some other substance that has the potential for being a magnet. Iron, nickel, cobalt, those are the three biggies that can, but there are other substances that can be magnetized as well. But if you put them in a strong magnetic field, so you sit this magnet near some giant magnet that's creating a huge magnetic field, over time, all of these magnetic field directions in the different crystals, the different magnetic domains, will start to all point the same way. And that is because the electrons will start spinning in there and spinning in the same direction and all pointing with their axis of spin in the same direction. So all these mini magnets are all lined up. So all the magnetic domains become one big magnet as a result of adding up all these individual fields. The other way to do it, which is much simpler, and you can actually do this at home if you want, you could take a needle or some piece of unmagnetized metal and take a magnet that you might buy in a store and literally stroke the magnet over and over on the needle. or some other chunk of iron, and just stroke it and keep stroking it. And over time, you will also line up the magnetic domains in the needle or whatever you're stroking, any other chunk of iron you have, and you will line them up over time. And if you do this long enough and with a strong enough magnet, you can create a permanent magnet out of it. If you don't do it too long, they'll start switching back, and then you'll have what is really a temporary magnet. But you can make permanent magnets this way. If you use a good enough magnet to do it and you stroke it long enough, you can line them all up, and they'll stay for a reasonable period of time. All right, so permanent versus temporary magnets. Permanent magnets, the domain alignment will remain, all be pointing, all the domains will have their magnetic moment pointing in the same direction. That's what we call it, a magnetic moment, magnetic direction, magnetic field direction. They'll all be pointing in the same way, even once you pull away the big magnet that you're either sitting it near or rubbing it with. If you pull it away and it keeps that magnetic field pointing all together, that's a permanent magnet. A temporary magnet, once you remove the other magnet or the other magnetic field that's near it, and it suddenly switches back to being random again, that's a temporary magnet. And there are lots of ways of making temporary magnets. You just do the same thing for with a little less intensity, a little less time. You can make metal magnetic, but if you don't do it for a long time, it'll switch back eventually. All right, so magnetic domains in a chunk of metal shown at the top here. This would be a typical unmagnetized piece of iron. You have a bar of iron that's not a magnet. All the magnetic field lines are all pointing in different directions. That north to south arrow, they're all different. If you start putting it in a magnetic field, they'll start to line up. So that second picture, you can see that the arrows are starting to all point in the same direction. Not quite. You give it more, a stronger magnet that's nearby, a stronger magnetic field, and eventually they'll all line up, and you'll make this into a permanent magnet. So once you have a permanent magnet, remember, we said that there's no such thing as a monopole. You can't have just a North Pole and a South Pole. So if you actually were able to cut this magnet in half, you'd end up with two new magnets. You wouldn't end up with a South Pole on one magnet and a North Pole on another. You'd end up with a smaller magnet that has a South Pole and a North Pole, and another smaller magnet that has a South Pole and a North Pole. And the one that used to be south is still south, the one that used to be north is still north, and the other one that was formed will be the opposite of whatever's on that particular magnet. It'll just be a little bit weaker, but the two new magnets will be the same strength as each other. So, as I've already mentioned to you, there's a definite connection between electricity and magnetism. These are intimately locked in with one another. Electricity can be used to create magnetism, and magnetism can be used to create electricity. So this is an example of electricity, electric current being used to create magnetic fields. And it turns out if you have a current, so you have this wire, and the current is running through the wire, and if it's running vertically, and when I say current, we'll call it current. Current in this case, because of Benjamin Franklin, current means the movement of positive charge. So the actual current would be this way with the electrons pointing down in that case. But it turns out if you want to know where the magnetic field is, you can take your right hand, point your thumb in the opposite direction that the electrons are going. In other words, the direction of the current, according to Ben Franklin, and curl your fingers around. You have to do this with your right hand. It only works with the right hand. If you curl your fingers around, it'll tell you the direction of the magnetic field. It'll be the north to south direction as you curl your hands around. And those field lines will make compasses move that have their own individual magnets. And the compasses will line up, the length of the compass needle will line up with the magnetic field lines that will go around this electric current. So you'll actually get rings of current around the wire. So if you have the wire with the current going up and down on this thing, you'll have the circle of magnetic field lines, and there'll be another circle outside of that, another one outside of that, and they get weaker and weaker as you go further, and denser and denser as you get closer because they're stronger. But they're rings around this linear stretch of wire that has current in it. Remember, this has to be moving charges for this to work. And if you reverse the field, the direction of the magnets will still line up. The magnets and the compasses will still line up, but the north and south of all of them will flip the opposite direction. So if you had this current going this way, and then suddenly you made the current go this way, all the magnets would turn the other way, but they'd still be lined up in a circle like this. They'd just all be pointing the opposite direction, north to south. So here's an example of a current carrying wire. On the top, it's just a straight wire. And if you imagine the current is going from the right side of the page to the left side, you follow the red arrow. That is the current as defined by Benjamin Franklin. In other words, we're making believe it's positive charges going this way when the reality is it's negative electrons going that way. So if you put your thumb in the direction of the current, not the direction of the electrons, in the direction of the current, and then just curl your fingers with your right hand, it only works with your right hand, it'll tell you where the field lines are of the magnet. You can actually curl it around and show yourself where those concentric circles are that wrap around the length of the wire. But what happens when you curl the wire? Well, now you have curlicues in the bottom here that actually wrap around the curl of the wire. So you can see that now you have field lines that are coming out from the center of that little loop and then going back on the sides of that little loop. And it depends on which side of the wire you're looking at and which way the current's going. But essentially you've got you've got magnetic field lines coming through the center of the loop and then going the opposite way on the outside of the loop as they loop around the loop. So you have this pattern of direction of magnetic lines that go around the direction of the current line. And you can actually see this when you take copper wire, put a current through it, and if you have it set up so it's going through a table or something, and you throw magnetic filings, iron filings down, you can see the magnetic field lines. So on the left here, you have that copper wire sticking through, and the current is going through it, through the wire. I can't tell if it's going up out of the table or down into the table, but you can see what's happening is the field lines of the magnetic force are making circles, concentric circles around that current. But if you make a loop of the wire in figure B, you see it's still making circles around the wire itself, but it's also coming through the loop. You can see the lines of the metal filings coming through the bottom, and they're kind of wide at the bottom. They tighten as they go through the loop, and then they spread out at the top. And then there are also lines that circle all the way around, so you get that field. And if you make lots of loops on the right here, now you're forcing a lot of the magnetic field through the whole length of the loops, and then they come around on the outside, and they come back through the center, and they come out the outside. And this is actually one way that electromagnets are made. If you have a lot of coils of wire where the current is going through them, maybe one long wire that's been looped around something or just looped by itself like here, you'll end up generating this magnetic field that goes right through the center and then comes out the sides and then goes back through the center again. And this is how electromagnets are made. Now, the intensity of these magnets will get stronger and stronger with two things. If you increase the current, that's how many electrons are moving per second, how many coulombs of electrons per second are flowing through the wire. The more charge you're flowing through faster, the stronger the magnetic field. But you'll also get a stronger magnetic field by just making more loops. The more loops you make, the more you're reinforcing all these fields from each loop. Each loop, like in B here, is producing its own field. When you line up a whole bunch of loops, now they all add up together to make one long line of these loops that are going through the center of the loop. And there might be a piece of metal. You could always put a piece of iron right through the center and have the wire coiled around that. And now your magnetic field lines literally go right through the bar of metal. And that's how you can make the metal turn into an electromagnet, but you don't even need the metal there. The field is already there without the metal in the middle. So electromagnets can be made by taking a bar of iron and wrapping a copper wire around it, or whatever is going to carry your current, wrapping it around as many times as you want. The more coils you put, the stronger the magnetic field. The more current you pump through the wire, the faster the electrons are moving in the wire, the more magnetic field as well. Now, in some of the superconducting coils that are used, say on this maglev train, this magnetic levitation train, these things move incredibly fast. They use superconducting magnets. They use magnets that are cooled down to just a few degrees above absolute zero, so that the resistance of the current is zero, and this allows the current to go through unimpeded without losing any energy. And they use these fairly good size coils that have coils of magnets around the coil, so the current is flowing all around these giant magnets. And there are many of these magnets along both sides of the superconducting maglev train, and these are used to propel the train forward, as well as to stabilize it left or right so it doesn't hit the rails on either side, as well as to levitate it off the ground by almost 4 inches. So it has all these magnetic fields created from these big magnets that are all electromagnets that are the result of coiling wire many times around these big loops, and then you generate these large magnetic fields. They're actually loops that form bigger loops, and then this magnetic field comes out of these, and this is what's used to propel the train, to levitate the train, and to stabilize the train. But these electromagnets, many of the electromagnets don't actually use even any metal in the middle. It's just the coils of wire that are producing these large electromagnets. So superconducting coils, these electromagnets that use superconducting metal, in other words, the metal's cooled down to super temperature so there's no resistance. Once you charge them up with a certain amount of current, and then you don't need to keep supplying voltage to make the current move. It'll just move. It'll just keep cycling through the wires forever, literally forever, as long as you keep them cold, and so they will generate magnetic fields for as long as you need them, as long as you keep the magnets cold. And these can be used in these magnetic trains, but it can also be used in large particle accelerators in giant physics labs like CERN, C-E-R-N. That's a giant lab in Europe that will accelerate charged particles like electrons or protons or other charged particles, more exotic ones, and it will make them, the magnetic fields can be used to move these particles at speeds that are close to the speed of light. But electromagnets can be used for more mundane purposes. The giant cranes that are used in junkyards to pick up cars, old cars, and move them into the crusher. Those are electromagnets. They're big hunks of metal that have been magnetized because there is a lot of electric current around the housing of it that's coiled around and around and around, and current goes through that, and the more coils there are and the more current that goes through, the stronger the magnetic field, and you have a magnetic field that's strong enough to pick up entire cars. But these trains, this is the most fascinating use of it, and Japan really is leading the way in maglev trains, the magnetic levitation trains, using the magnetic fields to propel the trains forward at unbelievable speeds. The record is 603 kilometers per hour. I believe that works out to about 275 miles per hour. Or maybe slightly faster. I believe that's what it is. That's the record. But it also uses the magnetic fields to stabilize the car and to keep it above the ground so there's no friction. So it's a really amazing use of magnetic fields, and they're even building one of these trains between New York City and Washington, D.C. That's about 220, 240 miles trip, depending on what road you take. That could take anywhere from 4 to 6 hours, depending on traffic. This train is expected to be functioning somewhere around the year 2030. That's not too far off. And it is expected to be able to transport people from New York to Washington, D.C. in 1 hour. That's 220 miles in 1 hour. That is a remarkable achievement using these superconducting magnets in these magnetic levitation trains. But we also use them in MRIs and functional MRIs, the fMRIs. These are imaging devices used in hospitals to image soft tissue in people, sometimes in animals, and they use large, powerful magnets as well. And these magnets are created by winding wire around and around and around, typically about 10,000 times to get an enormous amount of current, but also enormous number of coils, so that the magnetic field that's generated through the middle of them is large enough to actually affect hydrogen atoms in your body. And these can be used to actually image parts of your body. All right, so an electromagnet can be made stronger by A, increasing the number of turns of wire, that's the coils, B, increasing the current in the coil, C, both, D, none. Well, I just finished telling you both the number of coils and the amount of current going through those coils will increase the magnetic field. The more coils, the more current, the more electrons moving, and the more cycles they're moving around, you'll get bigger and bigger magnetic fields adding up, and you can generate really powerful magnets as a result. More current means more electrons flowing through. More loops means more field lines of magnetic force going through the loops, and they add up, and you get these very powerful electromagnets as a result. So you have this current carrying coil of wire, that is the electromagnet. The magnetic field lines will go through the coil, through the center, and if you have a bar of magnet in there, they'll go through the bar of magnet and make the bar of metal magnetic as well. But it's the field lines going through the metal, through the center of the coils, and then looping back around the outside and back through, that is the magnetic field. So as we mentioned, the strength of the field can be increased by increasing the current and increasing the number of coils. So industrial magnets gain additional strength by having a piece of iron in the middle. They can get a little bit stronger, and they can be more stable if you have a chunk of metal for the coils to wrap around. But these superconducting magnets don't necessarily have metal in the middle of them, so it's not always necessary to get a magnet with a really, really large magnetic field. But the magnetic domains, if you do have an iron core through the middle, the magnetic domains of the iron core that weren't lined up before will quickly start lining up, and now it will become a magnet in the process, as well as this magnetic field all around it. So electromagnets without iron cores are typically used in these maglev trains, the magnetically levitated trains. And the levitation is accomplished by magnetic coils that run along the tracks. They have a pair of magnets on both sides, and then there are magnets in the trains themselves on either side of the train, and then there are currents that actually run underneath the train as well. And between this combination of these three different sets of magnetic fields, one set will propel the train, and it does that by having alternating magnetic poles on the train and alternating magnetic poles on the side of the train, and they're constantly switching direction. And what happens is you'll have one magnet from the wall and one magnet from the train that are repulsive, and it'll push the train forward. At the same time, another magnet that's just ahead of it is the opposite pole, and it's attracting that magnet forward, and that'll pull it forward. And then as soon as it gets forward, the magnets switch directions. So now the next one pulls forward, and the previous one is repulsive, and it moves the train at unbelievable speeds. But you also have magnetic forces that the train is sitting on that will stabilize it to a certain height. It'll actually lift it up against the weight of the train, the force of gravity of the train pulling down. The magnetic field will push up until it balances about 4 inches above the ground. And then you have a third set of magnets that are there to stabilize it left or right. And if they move too far to the right, a repulsion force of magnets is over here, and an attractive force is over here, and it gently guides it back, and vice versa. If it drifts over here, this magnetic force becomes repulsive, and this one becomes attractive, and it slides it back. So you have the stabilizing magnetic fields, you have the levitating magnetic fields, and you have the propulsion magnetic fields that move the train forward. So to keep these magnets cool, they actually use liquid helium on the trains to keep the magnets down to about 3 or 4 degrees above absolute zero, and therefore the resistance in the metal, in the current, is zero. So they just charge them up once, and they're good forever, as long as you keep them cold. So you have to keep supplying liquid helium and you have to have something that will keep the liquid helium cool, that requires energy. But the current is just going and going and going, so the magnetic force is going and going and going with no heat loss. So a set of coils, like I said, is on the undercarriage and on the sides that's levitating. It's more on the sides than it is on the undercarriage. And then you have this propulsion of alternating current and alternating magnetic fields, both repelling it forward and attracting it forward, constantly moving the whole train in its propulsion forward down the track hundreds of miles per hour. All right, so moving charges in a magnetic field will experience a deflecting force. We haven't talked a lot about this deflecting force. And these are forces where if you have the current going in one direction and the magnetic field going in another direction, especially if they're perpendicular, that is going to be the best deflection. And what will happen is if you have the electrons going this way and the magnetic field going this way, the electrons will start being deflected upwards against it. So they're all perpendicular directions. So if you imagine my hand here, I have got my index finger and the rest of my fingers pointing perpendicular to one another, and I've got my thumb sticking up. I don't know if you can see that. So it looks like you're shooting a gun, but you've got your fingers, there we go, got your fingers pointing to the side. Well, if one of these is the direction of the magnetic field, north to south, and one of these is the direction of your current, the direction of the force is perpendicular to both of them. And if your current is perpendicular to the magnetic field, well, then you'll get the biggest force pushing the electrons up. It'll actually deflect them upwards, perpendicular to the direction it used to be moving. So the biggest force difference will happen if the movement is in a direction perpendicular to the magnetic field. You'll get a little bit less deflection upwards or downwards, depending on which way these are aligned. If the magnetic field and the electric field are not exactly perpendicular, if you start making an angle with them that's smaller than a right angle, there'll be a little bit less effect. You'll get less of a force perpendicular to everything. But if they're in the same direction, if the current and the magnetic field are in the same direction, you won't get any force produced. They have to be perpendicular or have some component of the forces being perpendicular in order to get this force effect from the magnetic field on the charged particles like electrons. So that looks like this. So if you have an electron beam coming through a magnetic field, so if you had, say, a simple U-shaped magnet where you can have a north pole and a south pole, and the field lines are going from the north to the south, so our magnetic field is pointing between the two poles, okay? And then you have the electron beam pointing perpendicular to that. So you have one way and one the other way. The force will be perpendicular to both of them, in this case straight up. Well, if you've got the electrons coming in and then there's a force straight up, it hits it, it's going to start bending upwards. And that is due to this magnetic field force on a moving charged particle. So you'll see this deflection in the perpendicular direction. Now it will change direction. It will not increase the speed of the particle. It changes the velocity, because velocity includes direction, but it's not changing the speed of the electron beam. It's actually just bending its trajectory to a new trajectory. It's bending it upward in this particular case. So the reason an electron moving in an electric field doesn't pick up speed is A, magnets only divert them. B, only electric fields can change the speed of a charged particle. C, the magnetic force is always perpendicular to its motion. D, all of the above. Okay, so the highlighted word here is the reason. In other words, some of these may be true, but they're not the reason why the magnetic field doesn't change the speed of the electron. We're not talking about direction, we're talking about the speed. Well, A, magnets only divert them. Yes, magnets divert them. They will change their direction. B, only magnetic fields can change the speed of a charged particle. Yes, that's true. Magnetic fields can't change the speed, but the question is, why can't they? So B is true, but it's not the reason. It's just telling you something that the question is saying. C, the magnetic force is always perpendicular to its motion. And that is the answer. Because while all three statements are true, only C actually provides an explanation. Let me explain. Magnetic force is perpendicular to the motion of the electrons. So if the electrons are coming in here and you have the magnetic field here, the force will be deflecting it more upward. It won't be straight up. Because it's already moving this way, it'll be deflected upward. And that is because the force is only in the perpendicular direction. There's no magnetic force that's in the same direction as the electron. We're already moving. So they're not going to be sped up. They're just going to be deflected up. You're not adding anything to this direction that the electrons were originally going in. You're adding to this direction, so it's just going to bend them up, but they're not going to change their speed in the process. So no change in speed, but there's definitely a change in direction. If the magnetic field and the electric and the electron beam are perpendicular, that's the best. If they're less than perpendicular, that will still work. If they're completely parallel, it will not work at all. There'll be no deflection of the direction of the electron beam. All right. So magnetic force on a moving charged particle can change the particle's A, speed, B, direction, both or neither. Well, we just finished saying it changes the direction. It does not change the speed. Electric fields can change electric charges' speed. Magnetic fields can only change its direction. Electric fields can change the speed and direction, but magnetic fields can only change the direction. So that is because the force is perpendicular to the way the electrons were moving. If they're moving this way and you add a force this way, it's not going to change their speed, it'll just change their direction. And that's the idea here. So since force is perpendicular, that force can in fact deflect them. It will deflect them, but it's not adding anything to the speed of it. However, when it deflects them, it might deflect them in a wire as they're going around, so the force may actually change direction as the current is changing direction. The electrons may be going in a circle, and as a result, the field that's coming out, the magnetic field force, is still going to be perpendicular, but you'll end up with these field lines that circle around the current lines. So this is just showing you the same sort of thing, that depending on which way the current is flowing, and when they say current, they don't mean the electrons, they mean Ben Franklin's positive charge current. So we know that the current is really made of electrons, but when somebody says current, we're actually talking about as if we're making believe that it's positive charges flowing. So if you know the direction the current the electrons are going, the current is the exact opposite direction. So in the left case, because we have the magnet oriented one way, the deflection will be pushing it up, and in the case on the bottom where the magnet is turned around, the current the force will be pushing it down. But these particles that are moving, these electrons that are moving, remember, these might be moving not just in a beam like in the last diagram we saw. In this case, we're looking at current carrying wires that have current in them. All right. When the electrons are deflected, they're not moving out of the wire. So if they get deflected, the wires get deflected. You're actually moving the entire wire will be moved because of this magnetic force from the magnetic field and the electric field and their orientation. So the whole wire itself is actually pushed up or pushed down. And you can actually use magnetic fields to move wires physically. Now you might wonder, why would I ever do that? Well, if you make the wire into a loop, you can make the magnetic field make one part of the wire go down because the current's coming around one way, and then as the current's coming around the other way, that part of the wire will go up, and you end up actually rotating the wire, and you can make the wire spin. And if the wire is attached to something, you can make something else spin, and that's how an electric motor is created. So you take advantage of these charged particles, the electrons, in a wire, and how they're affected by a magnetic field that actually move the electrons, but the electrons are stuck in the wire, so the wire ends up moving and gets deflected by the magnetic field. So the direction will be perpendicular to the magnetic field lines and to the current. So if you got the current this way and you've got the magnetic field this way, you'll have the wire deflected this way or this way, depending on which way you have the current and which way you have the magnet. And if you have the current going around in a circle, one side will be deflected one way and the other side will be deflected another, and you can actually spin this loop of current. So the strongest, these deflections are strongest when the current is absolutely perpendicular. So you want to design it so the wires are exactly perpendicular to the direction of the magnetic field from north to south. Okay, so let's talk about how we can use some of these principles with some devices that have been developed. Electric meters can actually be used to detect electric current. And one way they can use that is by combining a couple different principles we've already learned about. If you have a magnetic compass, so a compass with a magnetic needle, essentially a tiny little bar magnet that has a north pole and a south pole, and it will line up and naturally point towards Earth's north magnetic pole, and you can have that floating in it. But if you bring a magnetic field besides Earth's next to it, you're going to deflect that needle. You're going to make it point in a different direction because there's a new magnetic field that's affecting the needle. And so if you have an electromagnet, which is basically produced as a result of a magnetic current flowing through a wire and through coils of wire, creating a magnetic field, that new magnetic field will deflect the old magnetic compass that's already lined up with Earth's magnetic field. So the current itself can generate magnetic field. That's what an electromagnet is. It's current winding around the wires. It generates a magnetic field, and it will overwhelm the Earth's magnetic field. Earth is a huge object that acts as a giant magnet, and this is because of the liquid core of the Earth. We have a solid core in the center, and then outside of that is a liquid iron nickel core that's always flowing with these convection currents, and that's the reason why we're moving the metal with its electrons. We're moving it around and it generates a magnetic field. But the strength of Earth's magnetic field, while it's important for things like compasses, it's actually not that strong a magnetic field. And even a simple magnet that you can buy in a $1 store is going to have a stronger magnetic force than the Earth does, especially when you bring it near another compass, another magnet. So you can overwhelm that field. And the larger the current that you use, if you had something generating a magnetic field by using an electromagnet, the larger your current, the larger your magnetic field that you can create, and the more deflection of the compass from what it used to point to at Earth's magnetic north pole. So the concept here is the stronger the current that's next to it, the more magnetic field it will produce. The more magnetic field it produces, the more deflection of the compass needle will occur. So if you have a device that just measures how far a needle is changed from its natural north position, you can figure out how strong the original current was over here that generated magnetic field to move it. And that's the idea of detecting an electric current using a magnet that is deflected by it. So we can take advantage of this relationship between electric field and magnetic field, and Johann Schweiger did this in the early 1800s. He invented a device that's called the galvanometer. The galvanometer was invented by Schweiger, but he named it after Luigi Galvani, an Italian scientist who was known for working with electricity and animals. He was interested in bioelectricity. Specifically, he was interested in how electric sparks, electric current, could be used to make the legs of dead frogs actually move. He would put a current next to the leg that had been removed from a frog, and he could actually make the leg move around due to exciting the nerves in the frog. And he was studying this. In fact, Galvani was fairly well known for this to the extent that Mary Shelley, this is the young lady who at the age of 19 wrote and created the story of Frankenstein. She actually later claimed that she was inspired by the work of Galvani when she wrote her story. But Schweiger named the device after Galvani. It's a galvanometer, and a galvanometer is a current indicating device. And if we look at this instrument, you can see that it looks like a horseshoe magnet with something in the middle of it. And that's exactly what it is. He took a horseshoe magnet, so there's a north pole and a south pole in this magnet. There's magnetic field between there that would affect anything magnetic, and he has this needle on there that would be affected by it. But he also has in the middle, between the two poles of the magnet, he has this coil of wire that can be attached to something that would produce current. And if you attach that through there and you run current through the coil, you will create a second magnetic field that will deflect the needle in a different direction. And depending on how much the needle is deflected, you know you created so much magnetic field, and he could calibrate this to a certain amount of current flowing through the wire, so this device could be used to actually detect current that would be attached to this. And when you detect current, galvanometers are called ammeters, meaning you're measuring amps or amperes. This is the unit of measure for current. So it's also called an ammeter, but when you switch a button on these, typically, it'll just multiply whatever current it measures times the resistance of the device. And remember, resistance times current, a current times resistance, I times R, is equal to voltage. So the same exact device can be used to measure voltage, and typically you don't have two different boxes. It's usually one little box, and you flip a switch and it reads current in one mode, and you switch it and it'll read voltage in the other. But it's just two different versions of the galvanometer. Some people will call them voltmeters. You hear them called voltmeters more than anything, but any one of these three names is really the same thing. You've got a permanent magnetic field, and you've got an electric magnetic field overwhelming that magnetic field, so it makes the needle move, and the needle will move more with greater current and greater voltage, and it will move less with less voltage or less current. And so you can actually measure the strength of current using a device like this. So the device on the left here is what Schweiger originally invented. They now look like these boxes shown in the bottom here. Okay, so besides the galvanometer, there are other devices that take advantage of these interactions between electric current and magnetic fields. So in an electric motor, this takes advantage of a permanent magnet again, so you have some U-shaped magnet that's generating a magnetic field between the two poles of the magnet. And in this case, we have a very stiff loop of wire that's sitting between them. And this loop of wire is attached to some voltage source, like a battery here. But you'll notice the contacts to the battery are not permanent contacts. The yellow loop you'll see in this diagram is attached to these two pieces. They're usually brushes that allow the loop to rotate in space between the poles of the magnet. And when it does that, when it does rotate, it'll switch which side of the loop is attached to which wire from the voltage source, from the battery. Now, why would the wires even rotate at all? Well, the magnetic field will affect current. We already know that if we have charges that are flowing in a wire, and those are perpendicular to the field of the magnet, the wires will be deflected because the electrons in the wire are deflected. So what happens is if you have a stiff loop, this square-shaped yellow loop here in this diagram, that's between the two poles of the magnet, one side of the loop will have current going in one direction, and because it's going around, the other side of the loop will have current going in the opposite direction. And because the two are in different directions, they will feel different magnetic forces on them, perpendicular to both the direction of the magnetic field and the direction of the current. And this will cause the wire itself, the loop itself, to rotate. One side will be pushed up and one side will be pushed down. But as you complete the rotation, the contacts to the current source, to the battery, will actually switch positions. And now the side that was going in the direction that would have been pushed up is now going to be pushed down, so the wire will continue to rotate, and every time it rotates half a turn, it'll switch which contacts to the battery are going through it, and the current will switch direction, and therefore which side is being forced up and forced down. So one side, as a result, the side that's always on one side of the magnet will always be pushed up, and the side that's always on the other side of the magnet will always be pushed down. And this will result in the loop rotating extremely fast. And if you attach this loop to something else, you can rotate that really fast. And that is in essence what a motor is. You have something that differs from the galvanometer. It's not just deflected a little bit. The loop is actually deflected completely around halfway, and then the current switches, and now this side is being deflected this way. So this side was pushed down, this side was pushed up, this is pushed up, and now this side is being pushed up, and this side's being pushed down. So the thing will continue to rotate, and it will spin very fast, and you can turn a rotor with this, and that is in effect what the electric motor is. And because this wire is always reattaching to the current system, to the system that's providing current, that's providing voltage, you're essentially changing the direction of the current every half turn. Well, this is the same thing as an AC circuit. You're changing the direction of the current constantly. Every half loop, you're changing it. So it goes through this cyclic motion, both in terms of cyclic changes in the current. It's going positive and negative and positive and negative in direction, but you're also causing rotation, physical rotation of the actual loop. And this is how a motor works. Now, if you took the same setup and switched it around, you could actually use some kind of a hand crank. Instead of having a rotor that you're turning by this motor, you actually turn the rotor around. You will rotate the wire around in this magnet. And if this was attached to, instead of to a battery, to something like a lamp, you could actually rotate the wire yourself with the hand motion, and the wire being turned within the magnetic field will generate a current. Because remember, magnetic field can generate a current as well as current generating magnetic field that we saw in the galvanometer. So in the case of a device where we're actually cranking on it like a generator, we're providing the mechanical energy. In this case, we're not getting mechanical energy, we're pumping in mechanical energy. We rotate this thing, and then that will produce a current that can be used to power some device. So that would be the exact opposite of what an electric motor does. So an electric motor and a generator, and if you want to see the diagram of generator, it's in the slide, but it's also in chapter 25, which we do not cover in this course. So you wouldn't have seen this diagram until now. The electric motor and the generator are A, similar devices with similar equipment; B, very different devices with different equipment; C, forms of transformers; D, energy sources. Well, they're made of essentially the same types of equipment. They're just run in different directions. So they both use a permanent magnet, and they both have some stiff coil. And in the case of the electric motor, the current is provided by some battery or some voltage source that drives the current through the loop, and then the loop that would have been stationary if there was no magnetic force is rotated because of the force from the magnetic force. It's rotated, and that rotation can be used to turn something else, and that's the electric motor. But in a generator, we're doing the exact opposite. We're doing the turning of the loop, and there's no source of electric current in there except us turning it in the presence of a magnetic field, and that will generate current in the wire, in the loop, and that can be attached instead of to a battery that would take the current from it. We can actually produce current that can go to power something like a lamp or a heater or whatever we want to power. Now, in the case of the electric motor, this thing is spinning so much that even if you turn off the motor, this is what's in the blue text here. If you turn off the motor, this thing will still be rotating until it slows down eventually and stops. But while it's rotating, that magnetic field is still there, and it will actually still generate current, which is essentially what the generator does. So when you shut off a motor, it starts acting like a generator because it's already spinning. You don't have to crank it like a generator. It's already spinning. So they're essentially the same devices run in opposite directions. In the case of an electric motor, you're using electricity in the presence of a magnet to make mechanical rotational motion, the torque of the spinning loop. And in a generator, you're providing the torque and you're using the permanent magnet to create the electric current. So they both use the magnet. In the motor, you're using current to generate mechanical turning, and in the generator, you're using the permanent magnet, but you're doing the mechanical turning to create the current. So let's talk about Earth's magnetic field. Earth is a giant magnet. It doesn't mean it's super strong. It's just a giant magnet because it's the planet. Okay, and this is due to the motion inside the outer core of the Earth. If you look at the layers here in this cutaway diagram, the red represents the inner core of the Earth. This is a solid iron nickel core, but outside of that is a liquid iron nickel core shown in yellow in this diagram. And this flow of this molten liquid iron, this molten iron nickel will actually flow with these currents and vortexes in complicated patterns. And because of this movement with the charged particles that are part of this, you generate Earth's magnetic field. Now, I mentioned before that Earth's magnetic field is not the way people think of it is. The North Pole, what we call the North Pole, is actually the South Pole of the magnet of Earth. And that is because when we made compasses, we labeled one end of the needle that pointed north, north. Well, we're basically deciding what's going to be North Pole of a magnet and what's going to be the South Pole of a magnet by whether it faces north. So if it points to the North Pole, it's the North Pole of a magnet, or in a compass in particular, okay? But that means that the pole itself, the North Pole, is actually the South Pole of Earth's magnet. But we're still going to call it the North Pole. We'll call it the magnetic North Pole. It's not the geographic North Pole, the part that we would actually claim was the northernmost part in terms of latitude. If you travel north to the North Pole, that would be the geographic North Pole. The magnetic North Pole is where it's the northernmost point of the compass if you consider the Earth a magnet, and those aren't exactly lined up. And the magnetic North Pole actually moves every year, and it's been moving a lot lately. Eventually, it'll flip, so the whole magnet will switch, and what is the North Pole now will become the South Pole in terms of the magnets, and the South Pole become the North Pole. And this happens quite frequently. So the north on a compass, it's called north because it points north. But that's because the Earth's North Pole, the Earth's South Pole is really what we call the North Pole. And the magnetic field has reversed already 183 times just in the last 83 million years. That's a lot of reversals. We expect another one soon, but these reversals can take thousands of years to happen. They don't just flip overnight. So nothing horrible will happen right away. It's a gradual switching process, and it's not completely understood how this happens, but it's in great part because of the movement of this liquid outer core of Earth. So the magnetic field also protects the Earth. So the universe is really a shooting gallery of charged particles. We have particles that come from the sun. We call those the solar wind particles. But we also have particles that come from outside of our solar system and even outside of our galaxy. And these we call cosmic rays. Cosmic rays are really quite dangerous to astronauts who aren't protected against them. Most of the cosmic rays are protons, but there are some little bit bigger particles. There are even some negatively charged particles, but the bulk of cosmic rays, 90%, are protons coming probably from even outside of our galaxy, not just outside of our solar system, outside of our galaxy, traveling unbelievable distances, and they hit the Earth all the time. They hit everything all the time. And Earth's magnetic field helps protect us by deflecting these charged particles. Because they're charged and Earth has a magnetic field, when these particles come into the magnetic field lines of the Earth, which point towards the poles, one end, and then they curve around and point towards the southern pole, they deflect the particles, either deflect them completely away from the Earth, or they deflect them into the poles themselves, protecting the bulk of us on Earth from the effects of these charged particles. Not just the cosmic rays, but the solar wind particles coming from our own sun. Some of these particles get directed into the North Pole and into the South Pole, but a lot of them get deflected into regions that mimic the magnetic field lines of Earth's magnetic field. And these volumes of space around the Earth are called the Van Allen belts, named after a man named Van Allen who discovered them. And they're loaded with charged particles from both solar wind and cosmic rays. Originally, when people were first starting to go up into space in the late 1950s, 1957 is when we sent up when Russians sent up the first satellite, Sputnik, in 57. But then we started sending people in 1959, I believe, 1960, 61. In that period of time, there was some concern that going through the Van Allen belts might cause the death of astronauts. Luckily, they weren't there for very long, and they weren't exposed to too much. But these particles there are quite a few of these charged particles sitting there, held away from Earth, because we have this reasonably good magnetic field protecting us. And this isn't true of all the planets. Mars used to have a magnetic field, but it doesn't have one now. So it doesn't get that same protection that Earth does. Now, the storms from the sun, the solar wind that I just mentioned, they'll bring in lots of particles, and they're either going to end up in the Van Allen belts, or they'll be directed by the field lines of our Earth's magnetic field, and they'll be brought towards the poles. Well, because they're brought towards the North Pole and the South Pole, they end up getting pulled in by the field, and they're either trapped by the magnetic fields in the Van Allen belts, or they're actually corkscrew in and land in the northern latitudes of Earth or in the very southern latitudes of Earth. Well, when these charged particles are slamming into Earth, they're slamming into the atmosphere, and they cause disturbances with the particles that are already in the atmosphere, the nitrogen gas and the oxygen gas that makes up the atmosphere. So these ions that are coming from the solar wind and to a lesser extent from the cosmic particles, they come in and they start striking the nitrogen and the oxygen gas in the atmosphere, and they'll start causing it to glow like a fluorescent lamp. And this light that appears towards the northern parts of the Earth, we call it the aurora borealis. Aurora just means dawn, or the lights of dawn, and borealis is named after the Roman god of the north. So aurora borealis translates to northern lights, and you've probably heard that term. But you may not have heard of the ones on the southern part of the Earth, the aurora australis. The country of Australia was named Australia because the word australis means south. So aurora australis are the southern lights. So this happens on the southern part of the Earth as well as the northern part of the Earth. And this is because of all these high energy charged particles coming from the sun or from outside of our solar system, slamming into the nitrogen. And when they react with the nitrogen, they might produce blue light or deep red light. And when they hit oxygen, they excite it to produce green light and red light. Most of the lights that we see in these auroras tend to be green, but if you're lucky, you get to see some other colors. When I visited northern Michigan years ago, we would get to see the northern lights late at night, and it looked like curtains of green light in the sky. It was really quite remarkable to watch, and you'd watch these things waving across the sky as the particles would slam into the atmosphere and create these beautiful colors. So biomagnetism is the result of biological organisms, okay, that actually produce their own miniature magnets inside their bodies. And this happens with bacteria. There are some strains of bacteria, some species of bacteria that actually produce tiny crystals of magnetite. This is iron ore that is magnetic. This is the same iron ore that's found in the lodestones that were found 2,600 years ago by the ancient Greeks. And they're small enough that they're essentially made of a single domain of magnets. So a tiny magnet that they're created because they essentially added iron to them, and it crystallized in their body to form these tiny, almost microscopic magnets. And they would string them together to form bigger magnets in their body, and they would act as compasses in their bodies that they could respond to. So they use these compasses to detect Earth's magnetic field lines, because the little needles of magnetite, of iron ore, that these crystals in their bodies would line up with Earth's magnetic fields. So if they were in latitudes that were north, they would point towards north, but they would also point, remember, these magnetic field lines are kind of curved from the North Pole. They kind of curve out, and then they curve back into the South Pole. So the field lines would line up, the magnetite crystals, these miniature magnets in the bacteria would line up, and the bacteria would actually be able to sense the direction that these crystals are lined in order to navigate, and they would use them in order to detect oxygen concentrations that might be toxic to them, because of the way the crystals would line up in certain environments. But what's interesting is bacteria of these types of strains, similar strains that live south of the equator, remember they're closer to the South Pole, they would line up their magnets in the opposite direction. So they would be pointing to the South Pole instead of the North Pole. But bacteria are not the only organisms that can do this. Pigeons, especially some of these pigeons like the old carrier pigeons, which are now extinct, but pigeons that are known to be able to navigate over very long distances have been found to have multiple domain magnetite crystals, little magnets in their skulls. So these are slightly bigger crystals that are connected, and they're actually connected to a network of nerves in their brain, so that when they're flying, their crystals might align themselves with the magnetic field lines of Earth, and they can line up not only in the longitudinal direction pointing north and south, but because Earth's field lines around Earth are slightly curved as they go around the Earth, they would line up that way, and they'd be able to detect how far they are in terms of latitude, because of just how curved the lines are as they come around to the Earth. Remember, near the poles, the field lines actually start diving down towards the Earth itself. So they would be able to detect not just direction, but how curved they are, so they could figure out how far north they are, not just whether they're facing north or not. But pigeons and bacteria are not the only organisms that have been found to use biomagnetism. Other organisms have been found to use it as well, like bees and certain species of butterflies, certain species of sea turtles have been known to navigate using them, and even some fish. And with that, we'll stop here.